Hi, I'm Swarup Patel, course instructor for Geotechnical Engineering 1. In this presentation, we will go through determination of coefficient of permeability by laboratory methods. Laboratory methods for determination of coefficient of permeability are constant head permeability test and falling head permeability test. There are even various field methods like pumping out test and pumping in test, and indirect methods used for finding out coefficient of permeability are computation from the particle size and computation from consolidation test. To begin with, we will go through the laboratory methods for determination of coefficient of permeability. There are two types of tests. One is constant head permeability test, which is suitable for coarse grained soils, and second is falling or variable head permeability test, which is suitable for fine grained soils. Constant head test is suitable for more permeable coarse grained soil, that is sand, soil with high permeability. Here from the figure we can see that the soil specimen is placed inside a cylindrical mold whose length is L, and the constant head loss H of water flowing through the soil is maintained by adjusting the water supply. This soil specimen is placed between porous stone and rubber stopper on both the sides. The outflow water is collected in a measuring cylinder, and the time required for the collection is noted down. So after we apply Darcy's law, we get Q equal to KIA, and Q divided by time is equal to K into I is H by L into A. So K will be equal to QL divided by AHT, where A is cross-sectional area of specimen, L is length of specimen, and H is constant head, that is the vertical distance between water levels in the overhead and bottom tank. Second method is falling or variable head permeability test, and this test is more suitable for fine grained soils, that is clay, which is soil with low permeability. In this figure, we can see the arrangement for the test. The soil specimen is placed inside the tube and a stand pipe is attached to the top of the specimen. Water from the stand pipe is led to flow through the soil specimen. H1 is the head at time T1, H2 is head at time T2, and H is the head at time T. DH is the fall in head at that instant. The initial head difference H1 at time T equal to T1 is noted down, and water is allowed to flow through the soil such that the final head difference at time T equal to T2 is H2. Capital A is the cross-sectional area of specimen and small letter a is the cross-sectional area of stand pipe. Velocity of fall of water level V is equal to minus dH by dt. Flow of water into the sample, that is Q in, is equal to minus of A into V. So V is dH by dt. From Darcy's law, flow out of sample, that is Q out, is equal to K into IA, where I is H by L. From continuity equation, discharge flowing into the soil sample must be equal to the discharge flowing out of the soil sample. Q in is minus A into dH by dt, and Q out is KHA divided by L. So from equations 1 and 2, we get KA divided by L dt is equal to minus a into dh divided by h. So we will integrate this equation. We get a into integration of dh by h, which is equal to k into a by l integration of dt. Here the area of standpipe, cross-sectional area of the soil sample and length of the soil sample are constant. So they are taken out. Only the variables are the head and time t. So we will integrate them to get the equation for k. And in terms of log 10, k will be equal to 2.303 AL divided by 80 log of h1 by h2 to the base 10. Thank you.